Today we're going to take a look at extending the idea of derivatives with respect to x to taking derivatives of functions that have several variables in them. When there's more than one variable in a problem, what we're interested in is how we are changing in the direction of one variable or another. So we call these derivatives, where we're only looking at one variable, we call them partial derivatives. And when we're calculating a partial derivative, basically what we're going to do is we are going to treat all other variables as constants. So we'll use our derivative rules that involve constants. The derivative of a constant is 0, but if the constant is in front of a function, we just keep it in front of the function. So first we need a little notation so we know what we're talking about. There's about 4 different ways we can see a partial derivative. We're used to seeing f of x comma y to represent that there's 2 variables in there, x and y. And if we want the partial derivative with respect to x, we'll see a little subscript of x, or possibly a little subscript of y. And whatever the little subscript is the variable we're taking the derivative of. So if we are doing, for example, the first one, the partial derivative with respect to x, we will treat the y's like a constant as we solve with the x's. Similarly, if we're doing the partial derivative with respect to y, we'll take the derivative of the y's, treating the x's like a constant. So that's the first notation that you'll see. The second notation that you see is this almost curvy looking dz dx. And the curvy cursive looking derivative is the partial derivative of the function z with respect to x, or the partial derivative of the function z with respect to y. And so when we see the curvy d, that's the partial derivative, treating the other variable like a constant. You could also see just a z with a subscript of x or a z with a subscript of y to tell us to take the derivative with respect to x or y. And then one last notation that comes up on occasion is you see the curvy d with an f, curvy d with the x. Tells us to take the partial derivative of f with respect to x or the partial derivative of f with respect to y. So you'll see either any of these notations mean the same thing. Take the partial derivative, or the derivative of this variable, treating the other variable like a constant. So let's do a bunch of examples here. Let's say f of x comma y is equal to 5x squared minus 2x plus 3y squared. And we're going to find the partial derivative with respect to x. Now, if we're finding the partial derivative with respect to x, actually I'm going to change the equation, make it a little more interesting. We'll make that 2xy in the middle, 2xy. If we're doing the partial derivative with respect to x, that means we're going to treat all the y's like they were just regular numbers, regular constants. And so we look first at the 5x squared. We're taking the derivative with respect to x. We've done this before. That's going to be 10x. Minus, we've got 2xy. X is the only variable here. The 2y is a constant, so we just bring the 2y out front, and the derivative of x is just 1. Well, multiplying by 1 is not going to change it. The next term, the 3y squared, remember the y we're treating like it's a number. We've got a number times a number squared. There's no variables. This is just a constant number. Well, the derivative of any constant is 0. So that falls out, and we have the partial derivative of f with respect to x is 10x minus 2y. Contrast that with if we took the partial derivative with respect to y, Now we're going to treat the y's like the variable. Whoops, totally deleted them there. The y's are going to be the variables, so these x's are going to be treated like the constants. We'll treat the x's like they were just regular numbers. So the first term, 5x squared, there's no y's in there. Because there's no y's in there, we treat that like it's a big constant. Well, that's the derivative of that is 0. Then we see the negative 2xy. The 2x is a constant, so we keep the 2x, and the derivative of y is just 1. Plus the derivative of 3y squared. Y is our variable, so we bring the 2 out front, and we get 6y. And so we get the partial derivative with respect to y is negative 2x plus 6y. So the new thing we got to try and wrap our head around is treating the other variable like a number, like a constant. If the constants stand alone, the derivative is 0. If the constants are with the variable, then we treat them like we would any other number. Let's try some more interesting problems. Let's say f of x comma y is equal to 3xy times x squared plus y squared. And we're going to take the partial with respect to x. Notice we've got a product here. We've got the 3xy multiplied by the x squared plus y squared. So using our product rule, we'll take the derivative of the first with respect to x. So x is the variable, 3y is the constant, the derivative of the first, times the second, x squared plus y squared, plus the derivative of the second. In the second factor, we want to treat x like the variable. The derivative of x squared is 2x. Y squared, since there's no x's there, that goes to 0, times the first, 3x minus y. Same product rule, the derivative of the first times the second, plus the derivative of the second times the first. We're just treating the opposite variable like a constant. Cleaning up a bit, we've got 3x squared y plus 3y cubed plus 6x squared y. And we do have a like terms. Do it in a different color. 3xy squared plus 6x squared y is 9x squared y plus 3y cubed. We can also take the partial derivative of this with respect to y. Again, here we're going to take the derivative treating the x like a constant. It's still a product. So 3xy is the first factor. X squared plus y squared is the second factor. So we take the derivative of the first, treating the x like a constant. So we have 3x times the second, x squared plus y squared, plus the derivative of the second. This time we treat the x squared like a constant. It goes to 0. So we have 2y times the derivative of the first. I think I said that wrong. Times the first. Derivative of the second times the first, 3xy. So we have the product rule again. The derivative of the first times the second, plus the derivative of the second times the first. Distributing through, we have 3x cubed plus 3xy squared plus 6xy squared. This time the like terms are the other two factors, so we have 3x cubed plus 9xy squared for our final solution. Let's try another one. Let's say f of xy is equal to 3x minus 2y plus 4xy all over x squared y cubed minus xy. And we're going to find the partial. We're going to find the partial derivative with respect to x first. Now, this is a quotient, so we're going to have to use the quotient rule. We're looking for the derivative with respect to x, so we're going to treat the y like it's a constant. So when we do low, x squared y cubed minus xy times d high, the derivative of the top with respect to x. So 3x, the derivative is 3, minus 2y, there's no x's in there, so the derivative of that is 0, plus 4xy, the derivative of that is 4y. Low d high, minus high, 3x minus 2y plus 4xy, d low, the derivative of the bottom, treating the y like a constant. The derivative of x squared is 2x, and the y is just a constant, so it's along the right, minus the derivative of x is 1, and y is a constant, so we keep it. All over the low squared, x squared y cubed minus xy squared. And we can multiply this all out and just kind of see what we end up with. So the derivative of z with respect to x, the partial. Distributing, we've got 3x squared y cubed minus 3xy plus 4x squared y to the fourth minus 4xy squared. And to help with this negative so I don't get in trouble with it, I'm going to distribute it first. Negative 3x, positive 2y, negative 4. By distributing that, we get negative 3x times 2x y cubed is negative 6x squared y cubed. Positive 3xy. Positive 4xy to the fourth minus 2y squared. I'm hoping there's going to be some like terms that are going to make this a bit nicer. Minus 8x squared y to the fourth plus 4xy squared. All over the bottom stuff squared. Let's see, do we want to multiply that out? I guess we might as well. So when we square that, we got x to the fourth, y to the sixth, minus 2x cubed y to the fourth, plus x squared y squared. And now we'll see if there's any like terms. So we've got x squared y cubed. Any more x squared y cubes? There's an x squared y cubed. I think that's it. So 3 minus 6 is negative 3x squared y cubed. That one's an xy. Got another xy there. So negative 3 plus 3, that's 0. That's kind of nice. X squared y to the fourth. And an x squared y to the fourth, so 4 minus 8 is negative 4 x squared y to the fourth. Then we've got an xy squared, and an xy squared, negative 4 plus 4 is 0. That's nice. And then the last two, no like terms on them, plus 4x y to the fourth minus 2y squared. all over x to the 4th y to the 6th minus 2x cubed y to the 4th plus x squared y squared. I do notice we've got some GCFs we can take out. That's going to help us simplify. I do notice we have a GCF of y squared in the top. So we'll pull that out. It gives us negative 3x squared y minus 4x squared y squared plus 4x y squared minus 2. All over, we do have a y squared in the denominator also. That leaves us with x to the 4th, y to the 3rd. Oh, nope. 6 minus 2 is 4. Minus 2x cubed y squared plus x squared. So those y squares divide out, and we'll call this our final answer, negative 3x squared y minus 4x squared y squared plus 4xy squared minus 2 all over x to the 4th, y to the 4th minus 2x cubed y squared plus x squared. What fun that was! So let's do the partial with respect to y of the same problem. B, if z is equal to, same function, 3x minus 2y plus 4xy over x squared y cubed minus xy, we are going to find the partial of z with respect to y this time. So low d high minus high d low, square the bottom, and away we go. The partial with respect to y, treating the x like a constant. Low, x squared y cubed minus xy. D high, the derivative of the top, the 3x is a constant, that's gone. Then we've got negative 2 plus the derivative of 4xy, treating the x like a constant, is 4x, minus high, the top stuff, 3x minus 2y plus 4xy. D low, the derivative of the bottom, the y cubed is 3y squared, so we have 3x squared y squared, minus the derivative of xy is just x, all over the low squared, x squared y cubed minus xy squared. And in much the same way, we're going to simplify this guy, see what we come up with. Distributing, we get the partial of z with respect to y is equal to negative 2x squared y cubed plus 4x cubed y cubed plus 2xy minus 4x squared y. Again, so I don't get in trouble with the negative, I'm going to add the opposite and distribute that negative through the parentheses. That way I don't get in trouble with it. Negative 3x then times 3x squared y squared is negative 9x cubed y squared. Negative, positive now, 3x squared plus 6x squared y cubed minus 2xy, I'm running out of space, minus 12x cubed y cubed plus, this is terrible, I'm out of space here, plus 4x squared y, all over the low stuff squared, which is x to the 4th, y to the 6th, minus 2x cubed y to the 4th, plus x squared y squared. So let's find some like terms to clean this up. Partial of z with respect to y. We've got x squared y cubes. Got another set of them here. So negative 2 plus 6, that's going to be 4 of these x squared y cubes. Then we've got 4x cubed y cubed. And then over here we've got minus 12x cubed y cubed. So that's going to be negative 8x cubed y cubed. We've got an xy. And 2 minus 2xy's is going to be 0. That's nice. We've got an x squared y. And at the end, an x squared y. Negative 4 plus 4 is also 0. That's nice. And then just like before, our last two terms are not like terms. So we've got negative 9x cubed y squared plus 3x squared over our denominator of x to the 4th, y to the 6th, minus 2x cubed y to the 4th plus x squared y squared. And again, we're going to want to factor it to try and simplify the partial of z with respect to y. In the numerator, the only thing that we have in common is an x squared, so we'll pull that out, which gives us 4y cubed minus 8xy minus 9xy squared plus 3. All over the denominator, we've got x squared in common, also a y squared. The y squared, though, is not going to help us simplify. The x squared will, so we'll factor out the x squared. Gives us x squared y to the 6th minus 2xy squared plus y squared. And as we were hoping, the x squareds are going to divide out. So our final answer of this quotient is 4y cubed minus 8xy minus 9xy squared plus 3 all over x squared y to the 6th minus 2xy squared plus y squared, and we have our final answer. What made this problem ugly again? It's been our pattern all the way through our study of calculus thus far. What makes it ugly is the algebra. And the algebra wasn't hard, there was just a lot of it. We had to do a lot of distributing, combining like terms, factoring, reducing fractions. All that stuff we covered in Math 99, we're just doing a lot of it in one problem. The calculus is still the same. The derivative is low d high minus high d low, square the bottom, and away we go. So let's try another problem, maybe not quite as ugly as that one. Or maybe it is. We'll find out. Number 4. Let's say f of xy is equal to the square root of 2x cubed plus 3y squared. And we're going to find the partial with respect to x. Now what you might notice is we've got that square root, and we're used to ignoring square roots and thinking about them as 1/2 powers so that we can use that exponent rule. So with respect to x, again, it's going to be a chain rule. We've got some guts on the inside, but we know how to handle guts at this point. We bring the 1/2 out front times the guts, 2x cubed plus 3y squared, all raised to the negative 1/2 power, times the derivative of the guts. Well, we're taking the derivative with respect to x. So looking at the term with x, we bring the 3 out front, and we have 6x squared. The second term with the y in it, that's going to go to 0. There's no variables in there, no x's. And so to clean it up just a little bit, the 1/2 is going to move this stuff down to the bottom. So in the top, all we have is the 6x squared over 2 times 2x cubed plus 3y squared to the 1/2. And we have our partial derivative with respect to x. So let's find the partial derivative with respect to y then. Same idea, we've still got guts inside a square root or a 1/2 power, so we bring the 1/2 out front times 2x cubed plus 3y squared, all to the negative 1/2 power, and then we multiply by the derivative of the guts. Well, the guts, we're taking the derivative with respect to y. The 2x cubed has no y's. So that term goes to 0. The 3y squared, though, we know to bring the exponent out front, and we have 6y. And so when we simplify this, again, the negative exponent's going to move that stuff to the bottom. The derivative of z with respect to y, we have 6y in the numerator, and then a 2 and a 2x cubed plus 3y squared to the 1/2 power in the denominator. Let's do another one. Let's say f of xy is equal to e to the x squared y plus 3xy squared power. So all that stuff is in the exponent. And we're going to find the partial of f with respect to x this time. Well, we've got e to some stuff, e to the guts. We know the derivative of e to the guts is e to the guts, e to the x squared y plus 3xy squared. We just have to multiply by the derivative of the guts. We're taking the derivative with respect to x. So x squared y, the derivative of x squared is 2x, and the y is a constant along for the ride, plus 3xy squared. The derivative of 3x is 3, and the y squared is a constant along for the ride. And this is our derivative. Not much cleanup we can do. We'll call that done. So similarly, let's take the partial derivative of f with respect to x. I'm sorry, we just did x. Let's do with respect to y this time, so it's a different problem. That'd be more interesting. Well, again, we've got e to the guts is still the derivative e to the guts, a to the x squared y plus 3xy squared times the derivative of the guts. But this time our variable that's interesting to us is y. So in the first term, x squared y, the derivative of y is just 1, and the x squared is along for the ride. Plus the derivative of 3xy squared, the derivative of 3y squared is 2y, and the x is just along for the ride. And so our partial derivative with respect to y is this guy. Let's do one last problem, a problem with a logarithm in it, to wrap us up with these partial derivatives. We're really seeing all the same exponent rules that we've seen before. The only difference now is that we're treating the other variable like a constant. So if f of xy is the natural log of x cubed minus 7xy plus 2y squared, you might notice that this is the natural log of some guts. That's going to help us take the derivative. First, let's take the partial derivative of f with respect to x. Well, the derivative of a natural log of guts is 1 over the guts. 1 over x cubed minus 7xy plus 2y squared. We just have to remember to multiply by the guts, the derivative of the guts, with respect to x. So the derivative of x cubed, that's 3x squared, minus the derivative of 7x is just 7, and the y is a constant along for the ride. But the 2y squared, there's no variables there. That's just a number. The derivative of a number is 0, and so we stop here. Clean it up because we can put that second part over 1. When we put that second part over 1, we get 3x squared minus 7y over x cubed minus 7xy plus 2y squared, and we have our partial derivative. Whoops, too far. Let's do one more partial derivative then. Let's take the partial derivative of f with respect to y. Well, again, natural log of the guts is 1 over the guts, x cubed minus 7xy plus 2y squared. We just have to multiply by the derivative of the guts. Well, we're taking the derivative with respect to y. X cubed has no y's in it, so that's a constant. It goes to 0. The derivative of negative 7y is negative 7. The x is a constant. Along for the ride. Plus the derivative of 2y squared we know is 4y. And then similarly we'll clean it up by putting it over 1. We get negative 7x plus 4y over x cubed minus 7xy plus 2y squared. And we have our final solution. Partial derivatives. No real new derivative rules. Changing instead the way we look at the problem. If there's several variables, we look at the variable that we're taking the derivative of with respect to x, with respect to y. What variable are we using to take the derivative of? Treating the other variables like a constant. Take a look at the homework assignment, give it some practice, come to class with questions, and we will see you in class tomorrow.